呀，我重新录过的。重新录过啊！啊，录。对，好呀。你可以先。OK， 上来了。你 mute 掉你的 audio， 因为我懂。好的呀，我。OK. So CNC is basically machining, short for computer numerical control, which is a manufacturing process in which pre-programmed computer software dictates the movement of factory tools and machinery. This process can be used to control a range of complex machinery from grinders and lathes to mills and routers. With CNC machining, three-dimensional cutting tasks can be accomplished with a single set of prompts. Basically means that whatever you program in the computer, once you set it into the proper format, you just send into the proper machine, it will run on its own based on its positioning coordinates. That's CNC. So basically it requires two things. One is machine preparation, where once the operator has a readable file, like I said earlier, they can set up the machine itself, attach the appropriate workpiece and tooling for the program to execute correctly. Basically, it's more of a self-running machine. So you need process execution. With the files and machine prepared, the CNC can operate and execute the final process. They start the program, which then guides the machine through the entire process. So similar. So we go back to the history of CNC, which is at first in 1751, the first turning the machine with a metal frame was invented. This is where the industrialization begins. Back from 1751, moving on to 1947 to 1991, US Navy John T. Parson created the axis of a helicopter blades. Working with IBM, he studied the possibilities of controlling these machines by computer. From there, CNC machining method began. Up to 1952 to 1958, Richard Keck developed the first CNC milling machine. This basically is sort of like used for cutting, if I'm not mistaken, cutting out rods. So after that, 5 years later, he filed a patent for motor control apparatus for positioning machine tools, which is the old name for CNC. This is where the birth of this technology began. Okay. So in today's CNC technology, basically it is so advanced that it is used in many different applications like milling, breeding, lathe, even 3D printing is also actually one form of CNC. It is used in various industries like metal removal, fabrication, manufacturing, even cutting technology. It's self-monitoring, therefore it can be operated on its own as long as you give it the proper file. It can prevent collision on its own with proper settings. It reduces machining time and errors. Basically, it's sort of like its own AI where it can, as long as you give it new algorithm and hardware, it can be improved. In certain cases, they even include HMI graphics integration, whereby it's getting more advanced. So in types of CNC, I will go a bit more detail. So the first thing we have is CNC drilling. Drilling, I'm sure you all know what is drilling. Drilling is basically a technique where you make holes in unbroken surfaces. Unlike other methods, such as boring and tapping, in CNC turn components, drilling could mean drilling a simple hole or multi-feature hole, basically one hole, many hole is drilling. If you are able to design it on your software, basically it is possible to drill. So people may ask why we don't use conventional, traditional drilling and use CNC drilling. CNC drilling is more complex as one, it reduces work very easily, and you can keep repeating it for more and more, especially in big production. So for CNC milling, it is also similar to drilling, just that in a way that drilling basically drills a hole. Milling is basically where they take raw material and rotate a bit and slowly chip off material bit by bit of material until you get the finished product. It is a bit more complicated, but still with the help of CNC, it is still possible. And Then we have electrochemical machining. I'm sure by now you all noticed that there is something similar. It's just the CNC is the same thing. It's just that the application used, whereby either used for cutting or joining or even printing, is the same. So electrical chemical machining is a method of removing metal by electrochemical process. It is normally used for mass production and used for working extremely hard materials or materials that are difficult to machine using conventional methods. It is often categorized as reverse electroplating, as it removes material instead of adding material like normal electroplating. We have electrical discharging machine, EDM, is also known as spark machining or spark eroding. So what it basically does is that material is removed from the workpiece a little by a series of rapidly recurring electrical discharge between two electrodes separated by a dielectric liquid subjected by electrical voltage. This method is very effective, but unfortunately it is only limited to certain conductive material only, so still quite limited. So basically all is still the same, just that applications are different, so we won't go too deep in there. We have water jet. Basically, as you can see, it shoots high pressure water through a small little tiny hole. It produces a water jet able to cut even metals. And then we have plasma cutting, which is similar to water jet, but instead of water it uses plasma. And then we have laser cutting, which is also similar, but instead of plasma and water it uses light, focus light into a laser and just cut the material. So material selection. So basically, before you do any machining process, you need to know what material you are dealing with, whether it's wood, metal, or so. So we won't cover all materials, but we go by general. So first we have is what to consider when choosing materials. You have to consider how will the material be used, whether it is used in this way or that way. Is it suitable to use in that way? It depends. And then we have environment. For example, if we were to use something underwater, normally we wouldn't use iron because it would rust, or maybe we were to use in like high very stressed condition, we won't use brittle material. So it depends. So we have to consider stress load, basically whether the material can handle the stress, the type of fastening required, whether it's you're going to screw it, you're going to glue it, you're even going to rivet it, depends. And also we have to consider the high temperatures and the impact on the materials. For example, high temperature, we use plastic and then not long it's going to melt. So it depends. And then we also, important for most places, is cost. You have to see whether the material chosen is worth to be used. And then we also have to consider whether your machine can machine such a material or not. Basically, if your machine is a low powered machine, you would use hard material, then bye-bye machine. So we start with metals. Metal is a bit more simple because it's just depending on whether it's hard or soft. So as a general rule, softer metals like aluminium and brass machine easily will take less time to remove material, but in return it increases your time, the time you take to finish machining. So harder materials like stainless steel and carbon steel, they have to use slower RPM spindle and machine feed rate, as it would increase the cycle time versus the softer material. So as you can see this list here, okay, so the hardness, you can see it goes way harder. As hardness goes higher, RPM have to be reduced and feed rate has to be reduced. Otherwise you're just going to break your tool and break your machine. So I have to take note of that. So plastics are very wide variety and very general. So I will go just select a few common materials, alright? So I won't go too detailed. So plastics, we have ABS. ABS, I'm sure you know what's ABS. So ABS offers high impact strength, toughness, and electrical resistance at low price. However, it does not have good resistance to abrasion or chemicals, as it melts in acetone and it's not very strong. So plastic, in terms of general cut setting, I will go on later on, as you can see the pattern later as it goes. So acrylic is much more commonly used because it's a bit clear. So it's tough, decent impact strength and scratch resistance, can be glued easily using acrylic cement. And notice it can be glued in chloroform also, take note. So the drawback is that acrylic is a brittle plastic and it will fail by cracking or shattering rather than by stretching. So any machine surfaces on a piece of acrylic will lose their transparency and take on a frosted, translucent appearance. So mostly these kind of plastics are used for engraving, as from clear plastic, when you engrave in it, it becomes frosted, so it produces a very nice pattern. And then we have high density polyurethane. Now this is an excellent choice when it comes to chemical resistance, electrical insulation, and it has a slippery surface. It's well suited for making plugs and seals, and it's a good choice for weight sensitive and electrically sensitive applications. However, the strength wise is very poor, particularly in tension and flexing, so if you bend it a bit more, it breaks. So in plastic, generally you want to use a very high, ridiculously high speed rate and RPM rate, because if you focus your machining onto one point on the plastic, it will melt. If your spindle speed is too high on a certain point, or it's moving even by a little bit, it will melt as well. So you have to keep your settings high depending on the machine. For in this case, I set to 1000 to 1005, but again, it's dependent on your machine. If your machine has a good acceleration, you don't need to put it that high. My machine has a very low one, so I keep it high. So we have wood. Wood is a bit more general. So we have two different kinds of wood. We have hardwood and we have softwood. So I won't go do too detailed what is hardwood and what is softwood. By the name, you already know hardwood is hard, softwood is soft. Yeah. Hardwoods are more high quality and mostly used in furniture and construction that needs to last. So because it's more hard. Softwood is still commonly used, but mostly in doors and windows that produce more stress. So comparison, as you can see, hardwood and softwood. Hardwood has a darker color, it's more heavy, and obviously it's more expensive because it's harder. It lasts longer, it's more resistant to natural weather and more environmental impact resistant. So softwood is lighter color, lighter weight, far more less expensive. It lasts for long, but not as long as hardwood. It's weather resistant only when treated properly. So you have to, mostly they apply some sort of like coating over the softwood to make it last. So example of hardwood, we have ash, we have birch wood. So different woods, as you can see, they have different functions. Normally for CNC, you mostly see they use is cherry wood, mahogany wood, maple wood, and oak and walnut. Because these are more commonly obtainable. Some, for example, like elm wood is a bit harder to obtain, as it's a bit more expensive. Softwood is more or less variety, but you still have cedarwood, cypress wood, pine wood, redwood, spruce, and yew. Normally, commonly used ones are pine wood, because pine wood is easier to get and it's very light and it doesn't shrink. So, other than those woods, commonly used woods that you will normally find are MDF and plywood. Now, MDF is a multi-density fiberboard which is made from a mixture of hardwood and softwood and wax and resin binders. It's easier to work with CNC as you cut it, it produces a smooth cut. So it's more commonly used in like panels and backplates. So it's more of recommended use for MDF. Plywood is also commonly used, but it's a bit more tedious. It's basically made of layering sheets of wood together into one chunk of layer. The bad part about this is that when you strip off one layer, the second layer tends to chip off and cause it to splinter. So it requires a high skill to work with, but it's still doable. So we have now 3D printing versus CNC machining. You might, okay, so 3D printing, as I said, is also another form of CNC, but it's like the opposite of CNC machining, like drilling and milling. You'll see why in a bit. So CNC machining is a form of subtractive manufacturing, whereby you take a block, okay, you slowly remove material bit by bit. It's sort of like subtracting material. So to do this, you need to cut bits by bits off. So this is subtractive manufacturing. The opposite way is 3D printing is a form of additive manufacturing, whereby from nothing, you layers by layers are created. So basically you add more and more, and that's additive manufacturing. So to further understand, you can obviously see this picture. As you can see, you start with the material, you cut it off, you get the object. However, you end up with more waste, as you have start from material, definitely you have some waste. 3D printing is a bit more better, as you start with the material first, and it prints to get the object. You end up with less waste, far less waste. So you can see the comparisons materials wise. 3D printing uses metals, plastics, even living materials, as in medical now are so advanced that you can even print tissues, no problem. You can use it for, like, you can print bone replacement, tissue replacement. It's quite common. As for CNC machine, obviously you can't do with tissue. You only can do with metal, plastics, woods, and some other industry material. In cost wise, 3D printings are more cheaper, and CNC is a bit more costly because you need more power. Environmental, in terms of environment, CNC involves cutting away material. Upside down. Alright, I'll change it. 3D printing is additive manufacturing. In forms of object built on the platform. Basically, you feed the material, and you save a lot more material, but however, in some cases you need support material, which also consumes a bit more material. So depends on case. CNC, it's more non-environmental friendly, as it involves cutting away material from the original block. So there's always going to be a mess. You're going to have to clean it up. In terms of ease of use, CNC is a far more labor-intensive process. You need a skilled operator. You need to choose the correct tools. You need to know the correct rotation, the feeds and speeds. You need to do the correct cutting path. So it requires more skill. 3D printing, basically anyone can do it, as long as you know how to use it. It's more simple. All you have to do is just choose the file you want, choose the orientation, fill it up. If you need support, just add it in, and you're good to go. So it's a bit more simple. We go in depth to CNC. CNC machine follows the directions of the pre-programmed computer software. As I said earlier, it just follows when you teach it. The program specifies the machine's speed, movement, position to achieve a specific material shape. The CNC machining process features the following steps. First, working in CAD or CAD. The designer creates a 2D or 3D drawing in the computer-aided design or CAD software. This file includes specifications such as structures and dimensions that will tell the CNC machine how to create the part. So you have to be very, very specific in this section. Otherwise, if you don't tell your machine what to do, it's not going to do anything. So you have to convert the CAD file into a CNC code. Since the CAD file finds use in many applications, the designer needs to convert the CAD drawing into a CNC compatible file. Now, CNC compatible file, later on you're going to see how is it. It's something we call G code. It's the same thing in 3D printing. Okay, you just teach them. Normally CNC uses G code. It's quite common. So they changed the CAD format to a CNC format with such programs such as computer-aided manufacturing software. So as you can see, the software comes in a variety of types. We have CAD software. In beginner level, we have Tinkercad, BlockCAD, and FreeCAD. These are more simple to use, as the interface is much more simple. However, when it comes to complex designs, this will be hard to use. In intermediate levels, we have Creo and Fusion 360. Now, Fusion 360 is currently what we're using, and it's already considered quite a good software to use as the functions are quite wide range. Professional level, we have SolidWorks, AutoCAD, CATIA, OpenSCAD, and Rhino. These software are a lot more heavier and requires a better computer, and it's a bit harder to use, but with proper training you should be no problem. Now, types of CNC design, we have many kinds. We have delta. Delta is basically it moves only up and down. So basically you have 3 different motors at 3 different positions moving up and down. By this position you are able to move left, right, up, down in any position. So these are typically more accurate but they are however more expensive. We have a traditional Cartesian, which is XYZ. I'll explain a bit. SCARA is similar a bit to delta, however it moves in rotation. Basically XYZ, it only moves by rotating. So you can see it rotates here, here, and here. In polar, it moves also in in X and Z. However, it's missing one axis due to its rotationary base. So basically, one axis is in rotation. You just move X and Y, and just move Z and X. The bottom is rotating for you to fill up the rest. So you don't need one more axis. But however, in this training, we only will focus on Cartesian as our machine is Cartesian. The Cartesian CNC is based on a system of XY coordinates developed by a Frenchman, René Descartes, from Coleman, 1596. CNC machining that uses Cartesian coordinate system are based on the X, Y, Z axis. The system allows the machine to move in specific direction along a specific plane. Now, reduce the Cartesian system to its basic and you have a familiar number line. One point on the line is designated as an origin. Any number to the left are negative and any number to the right positive. I'm sure you've seen this before in elementary maths. Basically, how much you want it to move, just give it a number. So moving in 3 axes allows you to move it in anywhere. Now combine the X, Y, Z together at a 90-degree angle and you create a 3-dimensional space suspension. So each axis meets at the origin. So basically, you have the X, you have the Y, you have the Z. Any coordinates you need, you just change it as it goes. Now, using the Cartesian coordinate system, a CNC machine can be controlled. Each axis explain X controls left and right. Generally speaking, it doesn't apply to all machines, but generally, X-axis allows left and right, Y is moving forward and back, and Z is moving up and down. Now, this could be different for your type of machine, but this is generally speaking in most types of machine. Now put this all together and you have a machine that can cut not only various sides of workpiece in X and Y plane, but also various depths along the Z. So whether it's a milling, it's a router, it's a laser, they all use the same fundamental movements depending on orientation. Now we move to something more complex, is speeds, feeds and rates. This is the only complicated part about CNC machining, but once you get the hang of this, it should be walk in the park, simple. So we start with spindles. Now spindles, in case you do not know, I think I have something here to show you. Here's my spindle on substance. So spindle CNC plays a crucial role in machining. These components are fundamental to a fast and efficient process, while ensuring that the produced elements are precise as possible. They are available in a wide range of sizes to meet many different needs. A spindle is a device of a motor, a tapper for holding tools, a shaft that holds together all the separate components. Spindle rotates on axis, which receives input for movement from the accompanying CNC controller. Now, in case you don't understand, basically spindle is the thing where it holds the tool and starts spinning like crazy. That's spindle, right? It's normally will be at the Z-axis when it moves up and down. So it comes in various sizes. Not all materials can be worked by a single spindle of fixed rating. There isn't a spindle for everything. Proper speed and power has to be determined depending on the material. So if you want your spindle to work in a more variety of kinds of power and speeds and everything, you gotta get a very expensive one. So the spindle speed is a nominal value of the identification plate, depending on which RPM, normally comes in 12,000, 15,000, 18,000, 24,000 to 40,000 RPM, which does not mean the spinner is always spinning with these revolutions. Now, these revolutions are just stating its maximum revolution. You can alter it. Basically, you get a high power one, you supply it low power, it will move at the slower speed. Revolutions can be controlled by the inverter, but you have to remember that the spinner power is the value of the torque multiplied by rational speed, while preserving torque and reducing revolutions by about half the power also falls. So here you have to make a compromise. So take note that although you're using a high power spinner, you're not going to have a high power of torque, because torque and speed are basically not proportional. So you're going to have higher power, but you're going to have low speed. You're going to have high speed, you're going to have low power. So you're going to have to. So the second part is cutting speed, surface feet per minute, or commonly called SFM. It's also known as surface speed, or simply speed, which is the difference between the cutting tool and the surface of the workpiece it is operating on. So it's typically expressed in surface feet per minute, or the unit per unit time. Normally meter per minute is what we use. Revolutions per minute is basically measure of frequency of rotation. It is the number of turns complete 1 minute around a fixed axis. This normally we use the axis, the spindle. So high RPM means high speed, low RPM means low speed. Now, there is a relationship between SFM and RPM. So formula here, as you can see, your RPM is basically dependent on your speed and the diameter of your tool. So just follow this formula, you know what diameter of your tool, you know what RPM to use, what speed to use. So just bear that in mind. Feed rate is, or simply feed, is relative velocity at which the cutter advances along a workpiece. The unit are almost always distance per spindle revolution, or inches per revolution, or millimeters per revolution. Feed rate is important because it is directly related to virtually every aspect of CNC machining, from safety and productivity to tool life, surface finish, and part quality. It can also contribute to wear on CNC machine and mechanical components. So as I mentioned earlier in the material section, high speed rate, low speed feed rate, this is basically it. Basically how fast your material is going to cut into the workpiece. Faster one means it moves a lot faster, but bear in mind faster would normally cause more damage. Slow feed rate is always better, but it's not a really good optimization of time, so you have to take note of that. Plunge rate is basically similar to feed rate, but in the X direction. So basically you're going to move up and down, depending how fast. Now again, slow is always the best, but it's going to take a lot of time, so you have to calculate properly how much you need. That per pass is basically how deep your bit is going to be lowered each time you cut a material. So for example, let's say you're going to cut 5 mm of material. Now obviously you're not going to allow your bit to go in straight deep 5 mm, just cut the whole thing out. You're going to damage your machine, you're going to damage your bit, and you're going to eventually break something. So what normally we recommend you do is you do depth per pass. You do multiple depths, whereby you just cut one round. Maybe you, for each pass, you set 1 millimeter, and it's going to cut 1 millimeter around the material. Then it's going to go deeper, another millimeter is going to cut again. So you're going to go 5 cycles for 5 millimeters. It's going to take time, but it's going to guarantee a clean finish and save the tool. So another thing we have is chip load. Okay, this is going to sound very ridiculous, but you're gonna need to know chip load. Chip load is also known, also called chip tooth. Is basically the amount of material chipping removed by each fluke per revolution. It's basically, you know those things where you fly out after you cut something? Yeah, those are chips, and you're gonna have to take note that they're important. Now, why is it important? The proper cutting tool used with speeds and feeds information lets you achieve optimum chip load, basically less mess. Proper chip loads allows the cutting tool to move in and out of the material quicker, leading to more efficient CNC machining. To increase chip load, you need to increase your feed rate, decrease your RPM, and use a cutter with fewer flukes. Flukes actually. To describe, decrease chip load, decrease feed rate, increase RPM, and use a cutter with more flukes. Now, If you're not really keen on efficient CNC, it's not really that, it doesn't really matter that much, but it's best to have it, okay? Because if the part's going to come, you need to calculate how much chip load you're going to get. In order to know the proper feed rate, you're going to know the proper RPM and the number of flukes you need for the tool. Okay, so this is a table. Okay, it's in inches. You can change it to millimeters if you want. It's not like an issue. I can't find one for millimeters, so I'm just going to use inches. Now, depending on the material, hardwood, softwood, MDF, high pressure laminate, or paper stone, aluminum, acrylic, you're going to have different up to different types. You got 1/8 inch, you got 1/4 inch, 3/8 inch, and 1/2 inch and up. So it's not going to be very accurate. Just try as you can. So for example, here you can see the amount of chip load. This is given as chip load. You're going to know how much chip load you're going to get. So for example, let's say I was to use hardwood. I maybe use a 1/4 inch tool diameter. So I know roughly how much chip load I'm going to get. So from there you can know, maybe I'm going to use a tool with 3 flukes and I'm going to run it at 15,000 RPM. So basically you can know what kind of feed rate you need for your specific material and specific operation. So it's kind of useful, but as you go more and more, use more and more of it, your skills are better. You don't really need it. It's just for beginners, basic. Okay, just take note of something to do. Now this is basically a simple chart to better understand your feed versus RPM. Now, as you can see, feed is here. You have low feed, good feed, and high feed. You have low RPM, good RPM, high RPM. Now, low is always good. So if you start with low feed and low RPM, you're gonna get good stuff. It's just that it's gonna take a long time. You can grab coffee, you can go up and do anything you want. It's gonna take a long time, but you're gonna get good finish. Now, if you go up and you have a good feed and you have good RPM, it's called the sweet spot. This is very important as it is the best optimization of CNC you're gonna do. You're gonna do it just the right amount of time. You're gonna have a good finish. It's good. Now, as the feed is going up, you're gonna have, let's say, you have good feed but low RPM. You're gonna have a moderate surface finish, but it's gonna preserve your tool life. So the higher you go, obviously the tool is not gonna go very long. Now, a feed too high would result in your cutter overload and your cutter is gonna break. Your tool is gonna break. Now, similar with too high RPM, your cutter is gonna burn. You're gonna have like burns in your tool or even your materials. For example, if you're using wood, you're gonna see darker spots, or you're using plastic, it's gonna melt. So if you have used too high feed and too high RPM, obviously it's gonna have absolute destruction. You're gonna break everything. It's not really recommended at all. Don't do it. Don't try. Now we're moving on to motors and drive. Now, commonly used in CNC, we have stepper motors and servo motors. Now, these two are the commonly used ones. It's the only one actually. We'll see why in a bit. Okay, so both types of motor have several variances in terms of size and power. Following pros and cons of both stepper motors and servo motors are based on the comparison where both motors are equal power. So basically, we're comparing the same motor with same power to see its difference. In terms of cost, both CNC motors are very priced well. However, stepper motors are usually priced lower. Stepper motors are much easier to find, making them much more abundant. In terms of versatility, stepper motors are incredibly versatile, which makes them very popular among hobbyists and within industrial applications. Stepper motors can be found in thousands of products, from personal computers to automobiles. Reliability. What makes a stepper motor more reliable is compared to servo is the fact that stepper motors do not require an encoder. Servo motors are very reliable, however they require an encoder, which is also known to fail. So this is one of the reasons why it is more expensive, because you're going to need an encoder to run the stepper motor, the servo motor. In terms of lifespan, a stepper motor is considered a brushless motor and servos are brushed. So brushes normally would require to be replaced every maybe 2,000 hours after operating, where only parts that may wear on the stepper motor are the bearings. So you're gonna have to replace brushes here now and then with the servo motor, which again increase the price. Now, frame size, servo motors have a very large selection of frame sizes that they range from small to large. Stepper motors have a large selection, however, not as nearly as more as servo motors. So servo motor comes in more sizes, more selections, and more applications. In terms of design of servo motor is more complex as more internal parts and also the encoder. Stepper motors don't really require much, just the motor. Okay, now we move on to common linear drives system in CNC. So in case you're wondering what is linear drive, it's basically the thing that after you attach the motor, it's going to move something. So generally used in CNC, we have these few: lead screws, ball screws, belt drive, and rack and pinion. You might see others like rails and even higher end one. We're not going to talk about that because it's more uncommonly found. So lead screws are very commonly used. They're like the mother of drives. Lead screw uses the helix angle of thread to convert turning motion into linear motion. A large area of sliding contact between the male and female members of the thread generate relieve high frictional loss. So it's gonna heat up more and cause more friction, but the results of lead screw are less efficient as not as accurate as ball screws. It's low cost, it's ridiculously cheap. Just that the lead screw is a bit hard to find, so take note of that. Lead screws generally produce a very little noise as long as lubrication is maintained. So you're gonna have high friction, but as long as you oil it properly, it's gonna last quite a while, quite a long while. Now, however, these lead screws are good, they are cheap, but they come in. The problem is that it's difficult to use in long distance move, as you have to support only two ends of it, and the longer you go, it's obviously going to slop. So it's not really reliable for longer distance. The maximum people use is 1 meter tops. So if you're gonna need a bigger machine, you're gonna use something else. Now, those screws are typically similar with lead screws, just that they have balls. As you can see inside the nut, they have a bunch of ball bearings to decrease the friction. So ball screw consists of ball screw and a ball nut filled with bearings, high load carrying capacity. The use of large number of precision rolling elements also provides high level of accuracy. Now, low level of friction, which translates to high mechanical efficiency and reduced power transfer requirements. So, same. It also requires some lubrication, prone to noise, because you're going to hear a lot of balls moving around, so it's going to be noisy a bit. But it's an improved version of the lead screw. It's a lot better, but of course it's a bit more expensive because of the ball bearings inside. Belt drive system is also quite commonly used. Selected when high speed, high rates of acceleration and long slope lengths are most important criteria. Now these are normally used in 3D printers, as 3D printers require more high speed, offer somewhat lower speed and acceleration capability, so high speed, low speed works no problem. Low linear positioning of accuracy and belt drives, as might be expected, is not great as either lead and ball screws. In terms of accuracy wise, it's gonna wear off in a bit because your belt is gonna be stretched over time, so take note of that. Belt stretch as stiffness, drawbacks. Generally capable of high duty cycles, since they avoid concerns about friction and heat build up in the bearings. Generate relatively little noise and require relatively little maintenance. So in belt drive system, the only kind of maintenance you can need is changing the belt, which is not really big of an issue. It's just that you're going to change it quite a lot. My opinion said it's one of the best things, I guess. Offers a quieter running at high speed and higher load carrying capacity due to higher tooth contact ratio. So it's sort of like a gear system, only the other gear is a very long gear. Lubrication is very important, it ensures long life. Uses very little components, and accuracy is very high because it's using gear system. Gear systems are always higher. But however, it's high level of friction because metal and parts of it contact each other, but however, just lubricate it, it'll be fine. So it needs to run with clearance. Because it's using the gear system much, you're gonna have a bit of a backlash, but just a minor one, so not really big of an issue. So now we're moving on to building a CNC machine. Now this building a CNC machine is based on the CNC that I built here. It's not really a good one, the best of its kind, but it's a good one. So the goal was to build a CNC machine that has at least 800 by 800 of workspace based on this CNC Woodpecker 3018. 3018 basically means 30 cm by 18 cm of workspace. This is a cheaper version of desktop CNC you can get in basically anywhere for a cheap price. However, it's a bit small and a bit noisy, so there are ways to improve it. So the 3018 Woodpecker CNC basically consists of aluminium profiles and 3D printed parts. As you can see, consists of 3 NEMA 17 stepper motors, uses a lead screw drive system. Workspace is 13 by 18. Now the circuit itself is a self-built developer board that consists of Arduino Nano, 3 A498 drivers, and several other minor components, capable of both milling and laser cutting. So as you can see here, parts like these and these are all 3D printed. The rest is all aluminium profile, lead screws, linear bearings, and just rods. So the initial idea was just an upscale version of the 3018. It's not really much of a change, it's just bigger and more sturdier. The 3D printed parts were redesigned to accommodate larger mechanical parts. So basically what changes, the parts are still the same, but you just need more. 3D printed parts are changed a bit. However, the downfall, this idea was not really a good idea because it's quite expensive and it requires a lot of material, and I need a lot of material. So it was not really a good idea. The second design was a little bit better because it reduced as much parts as possible while remaining its stability. So most parts are 3D printed, including these corner parts here, the brackets, even the axis bearing spots. Now the entire machine was targeted at 1 meter by 1.1 meters. Okay. However, the idea was also further modified because obviously we're gonna have some kind of support. So to modify it to accommodate a sacrificial board, basically you're able to stick or screw in or stick your material onto this board and then start cutting it. So it was further then not a good idea because this support causes a lot of vibrations and most of the 3D printed parts start to crack and give away. So it has to be modified. As you can see, very much vibration from running it, and it breaks. It breaks very hard. So take note of that. Final design was similar to the second idea, however, more aluminium profiles were added for support. Basically, they support the y-axis and also the x-axis. The 3D printed parts were to slide over these aluminium profiles, preventing from shaking horizontally and vertically. Other than reducing vibrations, they also reduce the amount of noise, so which is a good idea. These are the supports that we added. Here you can see supports here and here and here. Parts used. Basically, first we'll start with mechanical parts. We have an LM10UU linear ball bearing. Basically, this is what we use to install inside 3D parts to allow them to slide over the metal rods, and therefore decreasing friction. We have a 10 mm deep groove bearing. These are basically used to support the linear screws, lead screws. As I mentioned, they require support at both ends. So one is attached to the motor and one more is attached to this. This basically allows the thing to turn freely without dropping. We also use the 8 mm trapezoidal anti-backlash brass nut. Now these are used normally with the lead screws. They're used to control whatever's moving on the lead screws, and because it's trapezoidal anti-backlash, it prevents backlash. So you don't have a lot of backlash in there, which causes inaccuracy in your cut. So we also have a 10 mm linear steel rod. These are basically the main supports of every axis. So as I mentioned, the linear bearing runs on it, so it requires a lot of greasing. We also use the 8 mm steel lead screw. Basically, this is the one used with the anti-backlash nut to drive motion. and the rest are just aluminium extrusions as support, basically the main frame of the machine. And we also have a 5mm to 10mm shaft rigid motor coupler. Basically, this connects the lead screw to the motor, so it's able to turn. Now, in terms of electrical part, our choice of motor here is the NEMA 17 stepper motor. Now, most of it will be used from the old 3018 CNC machine. However, because we're using a dual axis, we take one more from another broken printer. So this stepper motor can be used to control axis accurately. For the spindle, we're using a 77536 volt spindle. So high power DC motor used for rotating. And for the circuit board, we're using a CNC driver control circuit board. It's also known as a smart developer board. Consists of drivers and the brains of the CNC circuit. So as you can see here, we have the Arduino Nano, and we have the 3 drivers here. They're basically the A4988 drivers. We have the relay. These are their axis parts. Basically, it comes with dual Y-axis, so you can put dual axis in one. You have the Z, Y, and the X. You have the power for the spindle. You also have power supply here, and then you have some other parts. Now 3D printed parts, mostly parts are 3D printed because you want to save cost. So we have the angle support bracket. Normally this you can get already pre-made, but because we want to save cost a bit, we print our own, which are also very good quality. So it's to join the aluminium profiles at a 90-degree angle. Now we have the spindle holder. This basically holds the entire motor right here, and is responsible for moving the thing up and down. Then we have the Z-axis support. Basically, it controls movement of Z-axis, and it's going to hold the whole spindle holder. We have the Y-axis motor holders on one end. Basically, the motor is going to be attached on the other side, and basically your lead screw is going to be attached here and all the way to the other side to the X-axis support, where here you're going to mount the bearings and then your lead screw is going to go in. And you're going to have, for the X-axis, you're going to have 2 big chunks of support. Basically, as you can see, motor is going to be mounted inside here with 2 aluminium supports here going in and out. So mounted to the other side of the X-axis support. Now, in terms of controller software, controller software are very open source, and it's quite a lot of different kinds, but the one we'll be using is Gerbil or GRBL. GRBL is not an acronym, it's just a name, so it doesn't stand for anything. It's just commonly called Gerbil. I'm going to call it Gerbil. Gerbil's cute. GBRL controller is an open source software or firmware which enables motion control for CNC machines. We can easily install the GRBL firmware to instantly get a low-cost, high-performance CNC controller. The GRBL uses a G-code as input. As I mentioned before, CNC language is G-code, and outputs the motion via the Arduino. The GBRL used in this current version is the GBRL controller 0.8.1 version, as the developer board I'm using only supports this version. So before we start any machine cutting operation, we have to do some calibration. So as you can see here from this page, this is the calibration setting you will find in any CNC Gerbil connection. So every machine requires calibration on first setup to end, as it is essential to ensure accuracy for each operation. The configuration in the GBRL allows us to configure speed, acceleration, travel rate, and much more. By typing the $2 signs in the command bar, the settings for the CNC can be viewed and edited. Now, for explanation purpose, I'm going to explain every row inside here, so you all understand. Not all of them will be used, but most of them. So the important ones are like this. For example, as you can see, limit 20, 21. 21 here is for hard limits. Hard limits are basically, if you set this to 1, meaning you're adding limit switches. Now, limit switches you can attach to all axes, so to prevent your machine from over motion, basically moving too much and clashing into other parts. So you add a limit switch, which will automatically shut down all movements when the limit switch is triggered. Okay, and then moving on, we have a homing cycle, which is 22. Homing cycle is for more advanced machine. It's basically auto homing. The machine will home itself to the 000 origin, but of same you have to add limit switches or sometimes an electro bit. So it depends. Then you have one of the important ones, 100, 101 and 102. These are step per mm. These three things basically controls your accuracy of your machine. Now I'm going to explain this later on, so I'm not going to go into detail now. Then we have 120, 121 and 122. This is basically acceleration. Now as I mentioned before, feed rate is going to depend on this. For example, your machines, you're going to have, let's say your acceleration is high. For example, like this is 100. It moves 100 mm per second square. So basically, if you're going to have a high feed rate at this, it's going to move fast. But if you set this to low and your acceleration to low and your feed rate to high, it's going to move a lot slower. So you have to bear in mind that every time you set feed rate, you don't have to go 100% with whatever you see on net or calculate. You're going to have to depend on your acceleration rate set here. So then you can also set max travel rate to 100. Normally we keep it at 100. So you can depend, like if you want to move it more, you can set it more, but 100 is a secure baseline so that you don't overwork the machine. So, as I mentioned before, for configuration, the accuracy we have normally use a square accuracy method. Now to ensure accuracy, a square of 10 mm by 10 mm or by 1 mm deep is engraved on a piece of wood, not necessarily wood, could be anything, using proper bits and settings. The engraved wood is then measured to determine its real life dimension. So basically what you do is I have an example here. So as you can see, you can see we have cut a square here. This is not exactly 10 mm by 10 mm on the wood, but it's just an example. You engrave a square here. Okay. Once you engrave with the proper setting in the system saying that it's 10 mm by 10 mm by 1 mm deep, what you do is you take a vernier caliper, you measure the actual dimension of this. Let's say, for example, this is 9 mm by 9 mm. Alright. So what you're going to do is that you're going to, the value obtained is compared with the original value. By default, normally the three values are set at 800. So what you're going to do here is that you're going to do a bit of maths. Now, if 800 is going to give you 9 mm in reality, you have to calculate how much is going to give you 10 mm in reality. So a simple maths or dual ratio is going to help you get the proper value. However, you're not going to just do this once. You have to keep repeating it until it keeps giving you a consistent value. Because some values might be too much, some might be too low, so you're going to have to keep doing it until it's accurate. But over time, because parts are sure going to wear out, so you're going to have to keep doing this over and over after a period of time to keep your machine well accurate. Okay. Selection of bits. Now bits are quite complex, so I'm going to go even more detailed to other kind of bits just to cover up everything. So we have router bits, we have drill bits. Now drill bits, these are drive into material which are the best choice for task required material to be moved straight down through a piece. They're often used for pre-drilling holes or for screws. Now I'm gonna go very detailed about drill bits later. For now, we're gonna stick to milling bits. Milling bits or cutter or carving bits and end mills are used to cut laterally across your material. Now they are designed to move across the surface of the workpiece, clearing away chips to achieve 3D designs. So, factors to consider when you're selecting bits. First of all, material. Now you have to pay attention to the type of material you're going to use, the type and thickness. For example, you're going to use a thicker material, a very hard material, and you use a small bit, obviously it's going to break, so you have to really consider this. Cutting length. Always go for the shortest cutting length, because whenever the cutting length is longer than necessary, you're going to risk deflection of vibration and the inferior finish. Generally, the recommended cutting length should not exceed 4 times the cutting diameter. Otherwise, the bit's going to have a high risk of breaking. So basically, don't cut more than your diameter. Now, cut diameter is for quality finishing, increasing rigidity and the longer tool life use the largest tool diameter possible. Now you're gonna choosing diameter is sort of like a risk, because if you calculate using the formula, it's more of a safe zone. But if you're going by instinct itself, it's recommended you choose the largest possible because you're going to risk breaking it. Now, strongest bits, long bits are more susceptible to bending and vibration, while short bits tend to produce cleaner cuts. So when you're going to go for a longer bit, or you're going to set it that it's longer, you have to be aware that it might bend or due to too much stress. So shorter bits are more stable and you're going to give a cleaner cut. So keep it as optimum as possible. Now, sharpness of bits. Now, bits have many kinds. We'll go to that in detail, but the sharper it is, obviously you do better, but also it depends on your material. Sharp bits compared to dull bits are more quiet. They don't really produce much sound as it's going to be a clean cut. For milling bits, we have single edge bits. Now, single edge bits are used when speed is more important than edge quality. So this is basically, if you want to do it fast, you're going to use this. Now, these are commonly used for engraving. Double edge bits are used when quality is more important than speed. Now, this is going to produce a cleaner cut. The more flukes you have, the more cleaner cut it's going to be. V bits have a V shape on the end of the carving groove in your material. V bits are great for hardwoods and even better on engraving. But V bits, you have to be careful as the tip breaks off easily, so we use a stronger one. Upcut bits are used for slotting, grooving, or when chips need to be removed fast. Also suitable for when the material is coated or laminated on one side. Now, similar downcut bits are suitable for thinner materials. They leave a nice finish on the top, however chip extraction is less effective. So basically, upcut bits are going to drill into your material, and all those kind of chips are going to remove going up. Okay, downcut is going to leave all your chips inside that material. So top might be nice, but the bottom is going to be a bit jagged, so you can clean it up better. Now, ball nose bits are technically not sharp at all. So their bit end is rounded, which produce a path with curved edges. They are more for detail and cuts and engravings, in case you want a round edge, and then use a ball nose. I'm gonna show you another one first. Okay, we're gonna go to drill bits for a while. And you also drill bit lah. That's the slides on. Drill bit. Okay, so we're gonna go to drill bits a bit, just a tad little bit, just to cover up everything. So drill bits are normally classified into 4 kinds. We have solid carbide bits, polycrystalline diamond bits, carbide tip bits, and high-speed steel bits. Now, high-speed steels are more common. So first is solid carbide bits. Solid carbide bits are also known as tungsten. Now, tungsten is one of the most heat-resistant and strongest metal there is. Alright. Okay. Sorry. Okay. So solid carbide bits, tungsten. Tungsten is very hard. It's one of the hardest, strongest metal. So they use it in solid carbide bits. So since by the name you know it's solid and durable, commonly used for iron, heavy metals, and other abrasive metals. Polycrystalline diamond bits is a polycrystalline sintered body with vigorously screened synthetic diamond particles. Now, the hardness of these diamond particles are 80 to 120 times more solid than solid carbide, because diamond is the hardest material on Earth. So its thermally conductivity is high and coefficient with the thermal expansion is low. PCD is very hard and strong abrasive resistance. So it's very ideal bit, cuts about anything. So carbide tips are sort of like a cheaper budget version of solid carbide. So because only the tip is carbide, the rest is just normal steel. So it's similar with carbide. It can be used on harder materials, but only shallow cuts because only the tip is carbide. Steel is very common. It's a poured material, chemically and metallurgically bonded together. The steel is processed from raw ore and heated in a liquid stage where several units and elements are added to improve the internal structure. This can withstand a high temperature, and it's one of the most commonly used ones, suitable for low speed. Types of bit. For bits, we have twist bit. Twist bits are very commonly used because they can be used for typically anything. So we have can be used for wood, plastic, most concrete metals. So they're normally made for high-speed steel. They're quite sharp, normally used for drilling just about anything. It's very general purpose. Red point bits are primarily used for woods. However, some certain cases they can be used for plastics. The tip has a bit of a sharp end to provide accuracy for drilling. So normally with this you cannot exactly where the hole is going to be compared to normal tip bits. Masonry bits are normally used for drilling only concrete, bricks and stone, as these bits are, the tips are made quite tough, but often they wear down, so you're gonna have to change it quite a bit. 8 bits are quite sharp and big, so they're normally used to drill through wood and only wood. So as they leave a very rough hole, and then most often used to drill in areas that will be covered later. They are not generally visible because it's not going to be very pretty. And step drill bits. Step drill bits are used to drill up to 1/4 inch thick. Step drill bits are designed to enlarge holes that are already been drilled, so they're just going to make it bigger. So normally use wood, mostly metals and plastics. Auger bits are used to drill holes in wood. They're commonly used for boring holes into bulkheads and general timber applications. So these kind of bits only used for woods. So this product comes with a spiral bit head. When drilling is designed to pull the bits of wood, so you do not have to apply excessive pressure. And we have a hole saw. A hole saw is obviously for milling holes. It's basically a big saw with a bit in the middle, so allow you to have more accuracy in drilling the hole. Now, normally they come in a high-speed steel or diamond edge one, so it's going to be quite sharp and it can be used on mostly any material. Countersink bit is a cutting tool which puts a conical hole in the object, commonly used to allow the head of a countersunk bolt or screw is placed into the hole to sit flush with the below surface. So basically, when you're going to have a screw with the countersink head, basically these kind of diamond tip heads, you're going to have to use this to make sure it's flat on the surface. So you have no issue. That can be used on wood, metal, and plastics, no issue. Then we have a glass and tile bit. As the name suggests, you only can use on glass and tiles. It's used for drilling through glass, tiles, plastic, composite bricks, marbles, and hollow and bricks. It's a better resistant to high temperature, ideal for drilling through deep materials and speed up dust extraction. And I have threading bits. Now this is not exactly suitable to use for drills, but still a drilling bit. Now threading bits are used to create threads for bolts in materials like metals and plastics. Commonly used in engineering and manufacturing, threading tabs work is similar to a drill, but due to the unique shape of a tab, when screwed into a piece of metal, threads are created. Same used in plastic, woods, and metals. Bits, and I'll move back on to yeah. Alright. Alright, so now we move on to computer-aided manufacturing. Now we're approaching the end already, almost here. Okay, computer-aided manufacturing is basically the section where you have to teach your tool where to move, what to do. So in this one, we only going to be specific into Vision 360. We're not going to go too very deep. Other ones. So basically, the workflow works like this. It's just a simple 4-step operation. First, you're going to do setup. It's basically where you're going to do all the necessary steps to configure your machine. Operations is where you're going to teach your tool where to move. Simulation is you're going to check whether it's suitable or not, and then we have post-processing. Now these steps I will be even more detailed in the next slide, as we can teach you tutorial on how to use the machine, but that's later on. Okay. Setup is basically where you tell Fusion 360 which dimensions the stock material has, where the work coordinate system will be located. For every setup created, a different program needs to be made because the plane in which the machine will be working is different. So basically this is where you teach your machine, telling you where is the origin. Okay, Fusion's not going to do anything, so you gotta teach it how to do. So basically, as you can see here, we have a stock. The origin is come in the middle, so you're gonna have to tell it to move somewhere. Determining work coordinate system is where we define the origin on the location of the coordinate system that will correspond to the origin of the coordinate that is defined in the CNC machine. So as you can see here, when you press setup, it's gonna come up a tab like this. Obviously, operation type is gonna be drilling, depend on you. The orientation. Basically, you're going to choose orientation. Now here, origin and stop point, you're going to choose where you're going to set it. So as you can see here, you can add stocks. You can set wherever it is. You can add stocks at the side, top, bottom if you want, depending on you. Now operation for the most simple part, these consist of a simple toolpath and operations such as spacing, part, drilling, holes, making, and chamfer. Proper operations may vary depending on the user and the part. A list of common operations and their description can be found in such table. So we have a different kinds of variety to choose from, 2D or 3D. We have facing, basically removes one face of the part. We have a counter, using for removing like holes and fillets. We have chamfering to chamfer and fillet. We have pocket, mostly used for holes, big holes. And then we have drilling. Drilling is basically drilling. Simulation toolpaths in Fusion is extremely useful. Here you can optimize the machining toolpath and notice mistakes before they happen. Under the manufacturing tab, once the toolpath has been created, right-click on the toolpath and press Simulate to bring up the simulation workspace. Simulation will help you identify the potential to or machine crashes before they happen. So basically, after you created toolpath, we need to run the simulation to check whether it is optimum or not. Because sometimes when you create these paths, they're gonna sort of tend to clash into other parts, and then you're gonna come up with error. And you do not want that happening directly on the machine, so you have to run the simulation to check it out first. Other than that, sometimes using simulation, you can check whether your tool is like suitable for such purposes. For example, you're gonna make a very small cut, but you have a tool too big. So simulation is gonna allow you to know whether your tool is too big or too small. It's even vary. Post-processing. Now, post-processing is the last step into CAM. So once you have created and simulations are good enough, post-processing is needed. This is where Fusion 360 translates the toolpath operation into a variant of G-code language that your specific machine can understand. To post-process a program, under the manufacturing tab, click on the created toolpath or setup and then post-processor above the actions drop-down menu. So basically, when you click post-process, this is going to come out. Okay, you're gonna see generally post-configuration type of machine you're going to use. So for example, in our case, we use GRBL. You can set where you want to save it and what is the name, and the G code is going to be produced. It's going to be the same thing like 3D machining. That's all for guide to CNC. In a quick break, and then I'm going to show you, teach you how to use the CNC. Give me time to set up. Be back in 5 minutes. Okay.